Hey, it's Mr. Dean here, and we have another exciting video. This time, extreme values, brought to you by that 80s band Extreme, evidently. Extreme values are your collection of minimums and maximums, and they can occur, those minimums and maximums, at any interior point or any endpoint of your interval. For example, for our y equals cosine x function here, you can see that we have a maximum right up here at the top. That's 0, 1 actually. And we have a tie for minimums, and they're at the endpoints. And for cosine, those minimums would be negative pi over 2, 0, and positive pi over 2, 0. So there's a tie for the minimums. Taking a look at more minimums and maximum examples, here we have x squared graph. The domain goes on forever, both directions. You can see that it has no absolute maximum because the graph just keeps rising in both directions. It does have an absolute minimum, though, at x equals 0. So absolute minimum means the very smallest y value. Sometimes you have graphs who have a restricted domain. So same graph here, x squared, but the domain goes from 0 to 2, inclusive. So remember what those brackets mean. Those brackets mean, sharp brackets mean you're including that. And we have an absolute maximum now at 2, 4, and we have a minimum at 0, 0. So then you can have both. And sometimes you have one of these wacky domains that includes 2 on the right, but does not include 0 on the left. So you have an open parenthesis there. And when you have that, then you have no absolute minimum. There is no minimum here where you have an empty hole. All right, moving on. So taking a look, it looks like sort of a sine wave, I suppose, here. We have a maximum up here in the interior. And down here we have a minimum, and these are both at interior points. Over at this graph on the right, we have a maximum and a minimum. Both of those are on the endpoints. That's a possibility. We got all sorts of possibilities. You could have a minimum at your endpoint and a maximum in the interior. All right? And you could even have a minimum in the interior and a maximum over at an endpoint. So every combination is possible. So you do a combination of interior points and endpoints. On this graph, I want to bring your attention mostly to this strange spot right there. All right. So all the other spots are just kind of telling you that you have minimums and maximums, basically where the graph can go flat or an endpoint. All right. So this is an absolute minimum down here. Nothing is smaller. This is called a local maximum, just because it's the greatest value of f in the vicinity, anywhere nearby. Another local, there's a local minimum over here, and a local minimum on the endpoints there. But this absolute maximum, notice that this is undifferentiable. It looks to me like there's a cusp or a turn right there. It's not differentiable, but it's still, there's still an absolute maximum right there. All right, it's greater than any other y value on that graph. This leads us to the extreme value theorem, and I'll read it out to you. If a function is continuous, has to be continuous on a closed interval from a to b, let's say, so you have points at both ends and they're filled in, not an empty hole, then the function has both a minimum and a maximum value on that interval. It seems pretty self-explanatory, like you probably figured that one out yourself. It's basically saying every function has a maximum and a minimum, all right? Or it could have multiple ones. Here's a nice little function. It has a maximum on the endpoints. It goes from a to b, and the maximum happens to be at a, and the minimum happens to be at b. Now here's an exception on the right here, though. It does have a maximum up here, where it appears to be at a, c. But if we look for a minimum, we'll notice that there's an empty hole. It is not a closed interval, so it has an unknown minimum value. It's not quite like limits where we can say, oh, that looks like it was heading towards -3 or something. We just say it is an unknown or it has no minimum value, because the extreme value theorem says it has to be on a closed interval. All right. Now, to find the actual values, the actual numbers, if a function has a local minimum or maximum at a point and you're looking for it, as long as the derivative exists at that point, then the derivative has to equal 0. It's kind of neat. What it's saying is the derivative must be 0 right there. The derivative must be 0 right there. Now, up here, this is a cusp. Well, that's a different story. It doesn't have a derivative, but it's still an absolute maximum. And also at these endpoints, you'll see there's a local minimum there, absolute minimum there. So we have more than just finding where the derivative is 0. So to find all the extrema, we have to look at where the derivative is 0. All right, got it. That would be those two interior points. We have to look at where the derivative is not doesn't exist, which is up here. All right, that is a possibility for extrema. In that case, it looks like an absolute maximum for sure. We also have to look at the endpoints. All right, so let's take a harder look at what that all means. Critical points. So let's go back a bit. There's a lot of vocabulary in here. Critical points are any point in the interior of the domain in which the derivative is 0, or if the derivative is undefined. Those are called critical points. Extreme values then are a broader look at it all. Extreme values not only include critical points, but they include the endpoints as well. All right, so again, critical points are where the derivative is 0 undefined. Extreme values include those, and they also look at the endpoints. All right, so extremes again are minimums and maximums. Let's get right into an example. So let's find the absolute minimum and maximum of this function, which is x to the 2/3 power, and we only want to look, just because it's randomly assigned here, that the interval is between -2 and 3, and it's closed. So good, it's closed. So we will be looking at where the derivative is 0, and we'll be looking at the endpoints and where the derivative is undefined. So let's go. If we had a graph and we knew what the graph looked like, well, you just read it right off the graph, no problem. We can see that there is a local minimum over here, there is an absolute minimum at 0, 0, and we know there's an absolute maximum at 3, 2. But you're not always given the graph. So let's do it analytically. We want to find the derivative of that function. All right, so I kind of shortcut it here. Derivative is 2 over 3 times the cube root of x. And notice that it is undefined, the derivative is undefined, when x is 0, because you can't divide by 0. We can't have the denominator equal 0. That's not allowed. So when x is 0, that's one of our we're interested in that point. So let's find out what that value is in just a second. We're also going to find out what the value is at the endpoints. Remember the endpoints were 2, were 2 and -3. So back into it here. So at 0, at 2, -2, and at 3, we're going to find those. Once again, why are we doing this? We're plugging it back into the original function to find out what the value is there. And when I plugged in 0 into the function, I got 0 to the 2/3, which was 0. When I plugged in -2, I got the cube root of 2. I should have made that 2. We got a 0 there. When I plugged in a 3, we got 3 to the 2/3 power. I wanted to know what that was, so I got out my calculator. All right. So 0, I determined, is my minimum because it's lower than anything else. My maximum is 2.08 because it's larger than anything else. And the cube root of 2 is either a minimum or a maximum. They don't always have to be minimums or maximums. Let's check out another example, a little bit tougher. We have the functions a little bit more complicated. 1 over the square root of 4 minus x squared. We want to make sure of the domain. So when we're dividing, we want to make sure that we can't divide by 0, and we need to make sure that the square root is not a negative number. It looks as though the domain, when we figure it out, spend some time on it, it goes from -2 to 2. But no endpoints because it's not closed, folks. It's open. If we put in 2 in here or we put in -2, we are going to be dividing by 0. We don't want that. So we have to have an open interval. All the numbers between -2 and 2 can fit in there, but not on the endpoints. So I figured out I wanted the derivative to be equal to 0. I found out the derivative was this. And I was like, how is that ever going to be equal to 0? Well, it's only when the numerator is equal to 0 that a fraction is equal to 0. So when is this numerator equal to 0? Well, I found myself another critical point. Clearly, when x is 0, this whole function, function's derivative, is equal to 0. So we're good. We found some things. We got our endpoints taken care of. There weren't any values of the critical point, so we put in, back into my original function, I put in a 0. I got out a half. That is my minimum. Good question about how do I know whether that's a minimum or a maximum yet. And I have to just say we'll have to wait until the first derivative test. But you can do a little bit of a graphing or a little bit of plugging in and realize that that is the smallest number you can get out. We don't have to worry about endpoints as we said earlier because of what we had up here. And there is no maximum because, well, we only have one critical point. And we turned out when we plugged some numbers in, we found out that that was a minimum, so you can't have a maximum. And it's okay to not have a maximum. The extreme value theorem is not angry about that because it only works for a closed system, and this is open-ended on both sides. Again, more vocabulary. The difference between critical values. Now, don't think that your critical values are all extrema. All right, you find a critical value and you think it must be a maximum or a minimum. Well, that's not necessarily true. In this graph right over here, which is y equals x cubed, if you notice right in the center there, it actually flattens out all the way. The derivative right at 0 is 0. It's flat right there. But it doesn't mean that that is an absolute minimum or maximum. Of course, it's right in the middle of the graph. It's neither a minimum or a maximum. Over here on the right side, we have cube root of x. That also has a funny thing in there. The derivative there is not 0. The derivative there is undefined because it's a vertical line going straight up. The slope is technically infinity there, right, or undefined. And so that, again, that is not, usually you think, well, that must be a minimum or maximum if you don't see the graph. But you see the graph, and clearly, even though it's undefined derivative there, it's not a minimum or a maximum. Now, also notice in these two examples that the first derivative, first derivative is positive, right? Whatever the number would be, our first derivative here, positive is going up. Then it flattens out to 0, but then it's going up, up, up the whole way. Same here, the slope is up, up. Like it gets so, creeps so high, it goes to infinity for just a moment, but the slope is still positive the whole way. So in the future lessons, we're going to use the first derivative test to determine whether or not the critical point is a local maximum, a local minimum, or neither, but you're just going to have to wait around for that. All right, that's it. This is Mr. Dean, and we shall see you in class.